This webinar series is designed to give you updates on Croco, new features, new release, and tools that can be useful for the community. My name is Camille Mazoyer, and I'm a Croco developer working at the Institute of Research and Development at the MIO laboratory in France. And it's a real pleasure today to be co-hosting this session with my colleague Cyril Nguyen, who is working at the l'Aéro laboratory as an engineer in Toulouse, France, and he's here as a Croco developer. So Cyril will be leading today's webinar. He works with Francis Auclair on the non-hydrostatic part of Croco, and he is interested in small scales. So this needs a lot of computing resources, and coding GPU was a way of saving time. So today he will explain us how it works working with GPU. And just quick words about the logistic before we begin. This presentation will last around 30-40 minutes, followed by about 15 minutes for questions. So please feel free to post your questions in the chat as we go, and we'll answer them once the presentation is finished during the question and answer session, in the order they come in. And at the end, you can also use the raise hand feature if you'd like to say something, and you can ask for question in the chat. Now, so without further ado, so over to you, Cyril. Thanks.
Thank you, Camille, and welcome again to this webinar. Today we are talking about GPU on Croco. At begin, our primary motivation is in scientific ambition, because a significant increase in computing power will open the door to finer grid scale or longer simulation or large domain, or in complex physics contents. To understand why we are shifting GPU to acceleration, we can have a look at supercomputing center like IDRIS in Paris or NVHPC. The landscape evolving rapidly, and they massively acquire intelligence artificielle specialized hardware. So if we adapt Croco to this hardware, we can use these new resources. Furthermore, this GPU are available on our laptop or personal computer. This brings power in our desktop. GPU and CPU are very different. CPU is a general purpose and excel in sequential tasks. GPU come from gaming and graphical cards, and its architecture is driven by massively parallel computing. So there is actually no compiler that can compile and optimize the entire code to GPU. So we will need some few adaptation to exploit this GPU. Another interest of GPU is that energy consumption is proportional to its usage, unlike CPU. There is two main constructors of GPU, AMD and NVIDIA. We still try to use AMD a few years ago, but there is a problem with MPI communication between GPU and GPU in different nodes. And NVIDIA is much more mature, because about 20 years ago, they have the idea to use graphic cards for scientific calculation. And then they develop an entire ecosystem for their hardware with a compiler, optimized library for the graphic card, MPI optimized, and they have profiling tools. It works on Linux, and I think it works on Windows subsetting for Linux too. We decided to use OpenACC strategy to develop Croco to GPU. OpenACC is a directive-based programming model like OpenMP. It was very simple to use, and the first advantage is that we will have only one code for multiple architecture, and it worked fine with NVIDIA NV4 and G4 is on the road. Here is a simple example of OpenACC usage. The first thing we see is a kernel keyword. It's the principal kernel. It's the principal keyword when we want to use OpenACC. We put a loop in a region in a kernel region, and the compiler will compile for the GPU with very good performance. There is an example of transfer data from CPU to GPU, and the data transfer back from GPU to CPU. In Croco, all was for now handmade kernels. This means that we look at every loop and we put in kernel region. One important thing is that the data transfer between CPU and GPU take a very long time. So we adopt a strategy to deal with this data copy. We put all the Croco code on the GPU to minimize the data transfer. What we see on the right is one node of a cluster, and at the initial step, the data is the initial step in the main program. The data is transferred to the GPU, and the only transfer of data we can see is for I/O, for writing SCDF, for example, or for MPI I/O. Inside the node, data transfer are very fast because of new NVLink, for example, bus that which allow very fast communication between GPU and GPU inside the node. On the left, we saw a cluster with many nodes. Here we can see that exchange between GPU one node to one node is still more is more expensive. So we can see here the future problem, not really a problem, but the future explanation that in GPU scalability is not perfect. Now, after this introduction, the next slide will be more practical. I will show how to compile and launch Croco on GPU. I will show how we validate and performance result. And then with a synthetic view, we will look at how to change code or add routines, and then a few simple recipes. Now, to run Croco on GPU, what we need? We have downloaded the NVHPC toolkit with the NPI or NPI for the system. The only thing we have to do is to activate the OpenACC key. And then the job comp detects the OpenACC. And we compile it for the GPU. Here we can see in the job comp the additional option for the compiler. PG Fortran and NV Fortran is now the equivalent because NV Fortran, NVIDIA by PGI. Here we can see the option for GPU. Minus ACC tells the compiler to produce a code that will run on GPU. And the other option is to have a verbose mode. It's very, very useful. We have to be careful that sometimes on some cluster, nodes have not had the same hardware that frontal. For example, in Grasshopper, they are very expensive, and frontal is less expensive. So for the run, we have to compile the code on the node. To test our development, we have many cases, mainly a non-hydrostatic case. And we test, it deals with CVTK, which is okay. This means that MPI, we can reproduce exactly MPI simulation or the same result between CPU and GPU in the debug case CVTK. We also validate our development on a realistic test case, which is Gibraltar. In the next slide, I will show you results on the Basin test case. Basin is useful because you can change easily the number of grid points. Because we develop by hand, not all the CPP test case have not been tested. Sorry. In the next four graphics, we will see the same things in three different hardware. The test I made is on three clusters. The first one is in Laero, NUA, with an old Intel Xeon CPU and old NVIDIA VSAM. The second cluster, second and the third cluster will be on Occitanie cluster at Calmip, which is with their Turpan cluster and Kairos cluster. What we see here is on the bar chart is the number of grid points calculated by 1 second by one internal time step in Croco. What we can see that GPU begin to be useful if the grid is big enough. And on the hydrostatic case, I made two kinds of simulation, hydrostatic and hydrostatic. In hydrostatic case, we can opt to have about a factor 5 of acceleration. In a non-hydrostatic case, here it's on NUA, on all the Intel Xeon CPU and NVIDIA VSAM. In non-hydrostatic case, we can opt an acceleration by a factor 8. The difference is that in a non-hydrostatic case, the first step in Croco is in 3D, and going to CPU is equivalent to make the parallelization on the vertical grid. The same graphic on the more recent cluster with a RISC processor and an NVIDIA A100. The difference is better, and we can achieve in a hydrostatic simulation about 7 factor of acceleration about 7. Again, we have to have a big grid file for the GPU to be useful. The same with the non-hydrostatic case. Here I cannot show the CPU version because the queue is not long enough to run the simulation in my test. Here I show a resume of the last graphic, and we can see that the evolution in time with the cluster and hardware goes in better computing performance. The brown is our last cluster. We tested it about a month ago, and the results are very good. Again, I cannot show the CPU version because the queue was not long enough. But we have a factor 2 before the last GPU version H200 and H100. I made a test on a laptop, but I cannot show this because the laptop I made the test was 4-core and a small NVIDIA GPU. And if I put the result on the bar, it will be here. But on this laptop with 4-core and small NVIDIA graphic card is about 2 times faster than the CPU. We show that on one node, one GPU is faster than many core of CPU. Then now we are looking for the scalability. What we show is it's an older test that I made on Janzé at Idris with many node of 40 cores and 4 NVIDIA V100 GPU. We made the test about 1 node to 8 node. There is 2 tests, strong scalability and weak scalability. What we see is that the scalability is not good as CPU in GPU. As I said before, is because the communication between MPI halo between GPU and GPU. We can see that Croco in the CPU on weak scalability, the scalability is near perfect. At least on 8 node with 320 core and 22 GPU, the simulation with GPU is 2 times faster than CPU. Now we come on the development side. Usage of OpenACC is very simple. In Croco, we put all the data at the beginning of the simulation on the GPU. This means that in the subroutine main there is a call to copy to device. And in the common case, common loop can be accelerated to run on GPU by by putting loops under kernel. In common case, it's work very, very good. In common case, we have good performance only with this. But there is, for good performance, we have to make two changes sometimes in the code. For this, we had two kind of directive which are written in the change loop empire. What we can see, the first one is simple, is that the source code is here, and the change loop change the code in the version, in CPU version like this and GPU version like this. The problem of that code is that variable 2D variable fx and fe that don't parallelize very well because there is a race concurrence when you are on the vertical parallelization. So what the change loop does is that it transforms the 2D array in 3D array. And then you have a nice performance. The second change is more tricky. Again, with race performance on the vertical parallelization, you have to invert the do key, do high loop in do i, do kai. This will done with this key. The script change loop.py is called in the job scope and the make file. So when you see this case in the code, please don't change it. In general, in the day, I have three kinds of problems. The first two are very simple. What's happened frequently is that error. CUDA error out of memory. It's simply because I want to deal with too big grid on the GPU. It's not enough memory. The second one is that I forget to put to copy the new data on the device. So when you code something and you add variable, you have to, in the copy to device, put the data to copy it from the CPU to the GPU. And the third problem I frequently have, it's the code works fine, but performance are not so good. So what we can do, is look at the output of the compilation, which is very verbose, and we can look for sequential keyword. That means that the compiler cannot parallelize a loop and decide it. And now we have to deal with the algorithm to transform this. So when you want to use GPU, think big, because GPU loves big grid. I remember not all the combination in CPPDEF have been tested. Another thing, the numerics differ from GPU and CPU, not in the RVTK and debug mode, but because there is a vertical parallelization, the numerics can differ. An advantage of the GPU on cluster is the accounting, which is very profitable. And on personal computer, when the GPU works, the CPU have time to do something else. And now, what's about the future? The main problem with our development is that it's handmade development, and we have to include it in the GitLab say. And next problem will be maybe OpenACC. What will it become? Because AMD GPU is less expensive than NVIDIA GPU, but AMD still not maintain OpenACC directive. Maybe one solution will be to use a Cyclone, which is a Fortran to Fortran preprocessing. All the CPK had not been tested, but agrif is not yet in GPU. We have a reflection to CPU, because when you use CPU, CPU is still not active. What can we do with CPU in this case? And you have to work on scalability. One way is to explore MPI overlapping. There is a branch which tests it on the GitLab. It's all I see for now. If you ask question, I will be going. I will be here. Thank you.
Thank you very much, Cyril, for this nice overview of the GPU capacities. I don't know if you see it, but there's a lot of questions inside the chat. So people are wondering first if Croco version, which Croco version can we use for testing the GPU?
Master version still works, I think. I'm sure.
Okay, you're sure. Do you see the chat?
I read it just now.
Okay, great. So Biran asks, what is exactly the advantage of GPU over MPI? What do you choose? Why do you choose
have GPU,
GPI?
First, you can run GPU and MPI, but the scalability in MPI is not perfect. But what I see is that even with many nodes, GPU is still faster than CPU. Here.
Okay.
It's okay. Yeah, we can see
I
that.
think if Biran, you have more question about it, don't hesitate. Okay. So you think everybody should use GPU if you have a big grid over CPU?
Sorry.
You think everybody should use GPU if they have a very big grid over CPU?
Yes, if you want less restitution time, GPU will be more rapid. Okay.
Next question is from Sovara. So how much RAM do you have with your V100 GPU?
With the V100, we have 32 gigabytes.
Okay. Konstantinos asks if the GPU can run also with agrif, nested grids, and with submodels like sediments, biogeochemical models. If you can, did you test it? Because you say that you didn't test every keys.
No. So for instance, it just worked on no agrif, and it worked on the physical kernel, because we have a handmade, and we look at every loop and we put it into a kernel, the OpenACC kernel. So just physics.
Okay. So, but how does it work? If you use GPU with agrif and sediments and biochemical, will it work or
No,
I'm not sure.
no.
It won't work.
No.
Okay. Is it an idea for future or?
Yes. Yeah.
Okay.
Agrif is in reflection.
So if he wants to use it, he has to wait for the future
Yes.
improvements.
Okay.
Okay.
Well, you can do this.
Same question, more or less, from Swen. She's asking if it works with Oasis when you want to
Yes.
coupling with other models.
Yes. Joris, for example, Joris is on a method challenge, which there is a coupling run between MesoNH and Croco, coupling by Oasis. For this job, it's MesoNH which is on GPU and Croco on the CPU. The idea is to run GPU and CPU in the same time, and Oasis to coupling.
Okay, great. I think you answered the next question of Biram, because it was about MPI Noland and Agrif.
Yes,
so
it was
as you say,
Agrif, no.
Yeah, Agrif, it doesn't work, but maybe MPI Noland?
MPI Noland, yes.
Okay.
And XiOS too.
Okay, perfect. And so next question, maybe you read it. It's Swapnil Das, which asks if you run Croco QH quasi-hydrostatic successfully. I think it is.
I don't know. I never test.
Never test. Can you add test case in Croco? Okay, as an example. I'm not sure if I understand well the question. If it was just about Croco QH, he said that he wanted to add test case.
Okay.
You have a test case with OpenACC?
Yes, mini test case, but you don't have Croco QH. Okay.
Okay. And is it in the documentation, the test case with OpenACC?
I think there is Bassin test case in documentation.
Okay. Next question is about okay, the optimal ratio to where is the optimal ratio between number of grid nodes regarding the available GPU cards?
There is no real response because it depends on the time stepping and the number of NDT-fast. The internal mode of Croco is in 3D and work very well. The 2D mode less. So it depends. There is many factors.
Okay, for the it's for the NDT fast, for the time, the DT, and for the grid. And with the grid node, sorry, I'm not sure I understand. So people should test.
Yes, of course. Yes.
Try different.
You have to try. There is no.
And maybe we can have a look on the graphic you show.
Yes.
Also, to see the difference between CPU and GPU and.
Okay. The graphics show qualitative performance. We can expect a factor of acceleration by 8. I'm pretty sure, but maybe more. I'm not sure. On on CPU and on all the CPU and GPU card. I always have this factor.
So I read next question on the chat, and I see that Swen says that GPU is available since version Croco 2.0. So it's a master, and it's the version you can download from now. And you've got a link for the inside the documentation. So Swen give us the link. And Pierrick is asking if there is a bottleneck with the I/O. So you said it works with XiOS?
Yes, it depends. If you want to send I/O every time step, there is a bottleneck. If you send I/O every 100 time step, it will be okay. And second, it's the data come back to the from the GPU to the CPU with it's asynchronous. So if there is no bottleneck, if you're reasonable.
Okay, if the data have the time to be written, it's okay. It will be okay.
And
okay.
it could be you could have a bottleneck with the when you are with the file system to write the file, but not in when you run not in a computational mode.
Okay. Next question from Francesco.
Yes.
So the question is, how do you actually handle multiple GPU? Is it automatic, or did you code domain decomposition distributed on different nodes? And then each node you can use available GPU.
It's a domain decomposition and automatic. There is one domain by GPU, and if you can put more domain on a GPU.
Okay.
Again, it differs with the hardware. Sometimes, if you put 2 MPI domain on one GPU, it works better than if you put one domain on the one GPU. Okay.
And you say it's automatic?
Yes, it's automatic. With the MPI rank, you affect the domain to a GPU.
But you choose a number of decomposition domain?
Yes, in the param.h.
Okay. As in the MPI decomposition domain.
Yes. You just have to choose the MPI decomposition domain.
Okay. Next question. There's a lot of questions. The next question is from Harold, who asks if simulation with very small delta t values, can simulation with very small delta t values be regarded as large grids? I don't understand very well the question. Do you, Cyril?
I'm not sure, but I understand is a time step faster on GPU than a CPU. To my opinion, what I think is that on GPU, the frequencies between CPU and GPU is a limitation. You can do simply, with GPU, it's nice for big grid. I'm not sure you can.
But big spatial grids.
Yes.
Okay.
The time of 1 point grid on iteration is no more faster.
Okay. Sven gave us the link for the documentation more precisely here, if you want, in the chat. And Konstantinos asked, he said that NVIDIA H200 GPU is an expensive card. Can we have a performance gain with commercial cheaper cards? For example, NVIDIA RTX model. Is it okay with this?
I don't have NVIDIA RTX models. Just on my laptop, I have a RTX 250, but it's very small. We have all the Titan card, but it's have a long time that I don't use it, so I can. Okay, so I don't know.
Yeah, you didn't try.
No.
No. Mm.
We have.
So this can be try.
Yes.
With people can try. Mm-hmm. So sorry, Konstantinos.
Sorry.
Biran ask. Okay, it's a question in French. He has a laptop computer with 12 core. It's a Intel Core. But he doesn't have.
Yes.
Do you see the question?
Yes. The constraint is to have a graphic card and NVIDIA graphic card. Maybe AMD, you have to check GNU and OpenACC if you work well.
Yes.
All the tests we made is with NVIDIA and NVIDIA ecosystem. And you must have a graphic card.
You need the graphic card. Yes. So if you don't have one, you can't use it. What about CUDA?
The first time, yes. The first time we test GPU was on the NBQ kernel, and we code it in CUDA. But with OpenACC, we have only one code, and performance are still the same.
Okay.
Because the code is very simple for computing with many free loop.
And Konstantinos has a question. Can we have multiple cards? So is there a large delay in transfers?
Generally, on a cluster, on a node, you have at least 4 cards and sometimes 8 cards. And transfer inside the node is very fast from card to card.
So it should not be a problem. Okay,
but to use multiple cards, you have to use MPI and at least one domain by card.
Mm-hmm. Yes.
But if you use a multiple node, it works. But there is scalability is not perfect. Oh, sorry, I am on the last question.
Yes. Okay, thank you very much for all the questions you asked, and I hope that we answered your question. I think if you have more questions, you can ask them on the forum also. And thank you all for being here for the second webinar. I think we can stop it now. And thank you very much. The next webinar will be on June, and we will keep in touch 1 week before to tell you the subject precisely, and tell you the day of the webinar. So thank you very much, and see you in 2 months. Bye.
Thank you. Bye-bye.
Thank you very much, Cyril.